Welcome to Ask Prep, your trusted companion for NEET and JEE preparation. Today we will study about a very important topic of physics, which is Bohr's model and the spectrum of hydrogen. These concepts revolutionized our understanding of atoms and played a crucial role in the development of quantum mechanics. For centuries, scientists attempted to understand the structure of atoms. The early models of the atom, including Dalton's theory and Thomson's plum pudding model, provided initial insights but failed to explain experimental observations. Then came Rutherford's nuclear model, which proposed that an atom consists of a dense, positively charged nucleus with electrons orbiting around it. However, this model had a major flaw. According to classical physics, electrons moving in circular orbits should continuously lose energy and spiral into the nucleus, making atoms unstable. But we know that atoms are stable, which meant there was something missing in our understanding. This is where Niels Bohr made a groundbreaking contribution. He proposed that electrons move in fixed orbits around the nucleus, called energy levels. Unlike Rutherford's model, where electrons could move freely and lose energy, Bohr introduced the idea that electrons can only exist in specific, allowed orbits. They do not radiate energy while staying in these orbits, ensuring the stability of atoms. This was a major breakthrough in atomic theory. According to Bohr's model, electrons can jump from one orbit to another by absorbing or emitting energy. If an electron gains energy, it moves to a higher orbit, further from the nucleus. If it loses energy, it falls back to a lower orbit, releasing energy in the form of light. This process of electrons absorbing and emitting energy is the key to understanding atomic spectra. When an electron moves from a higher energy level to a lower one, it releases energy in the form of light. But what is interesting is that this light is not emitted continuously. Instead, it comes out as distinct lines of specific colors. This is known as the atomic spectrum. Each element produces a unique pattern of spectral lines, like a fingerprint, which helps in identifying different elements. The simplest and most well-studied atomic spectrum is that of hydrogen. When hydrogen gas is energized, it emits light, which, when passed through a prism, splits into a series of colored lines. These spectral lines are not random, they follow a specific pattern, which was successfully explained by Bohr's model. The hydrogen spectrum provided strong evidence that electrons occupy discrete energy levels, supporting the quantum nature of atoms. The discovery of atomic spectra was a turning point in physics. It not only confirmed Bohr's theory but also helped in the development of quantum mechanics. Scientists realized that electrons behave differently from classical objects and obey quantum rules, where their energy is quantized and restricted to certain values. Bohr's model, though revolutionary, was later refined with the advent of quantum mechanics. While it correctly explained the hydrogen atom, it failed to account for more complex atoms with multiple electrons. The modern atomic model, based on quantum mechanics, describes electrons as existing in probability clouds rather than fixed orbits. However, Bohr's ideas remain fundamental in understanding the structure of atoms and energy quantization. One of the most crucial postulates of Bohr's model is that an electron in a stable orbit does not radiate energy. This assumption was essential in overcoming the limitations of classical electrodynamics, which predicted that electrons should continuously lose energy and spiral into the nucleus. Instead, Bohr proposed that an electron can transition from one orbit to another by absorbing or emitting a discrete amount of energy in the form of a photon. The energy difference between these orbits determines the wavelength of the emitted or absorbed radiation. This leads to the characteristic spectral lines observed in atomic emission or absorption spectra. The spectral series of hydrogen was one of the strongest pieces of evidence supporting Bohr's model. The hydrogen spectrum consists of several series, each corresponding to electron transitions between different energy levels. The most well-known series in the hydrogen spectrum include the Lyman, Balmer, Paschen, Brackett, and Pfund series. The Lyman series consists of transitions where electrons fall to the n is equal to 1 level from higher energy levels and is observed in the ultraviolet region. The Balmer series, which is visible to the human eye, results from electrons transitioning to the n is equal to 2 level. The Paschen, Brackett, and Pfund series correspond to transitions to the n is equal to 3, n is equal to 4, and n is equal to 5 levels, respectively, and lie in the infrared region. The concept of atomic spectra has significant applications in science and technology. It is widely used in astronomy to determine the composition of stars. By analyzing the spectral lines emitted by distant celestial bodies, scientists can identify the elements present in them, giving insights into the universe's composition. Another important application is in spectroscopy, a technique used in chemistry and physics to study materials by examining the light they emit or absorb. Spectroscopy is essential in fields like medicine, environmental science, and forensic investigations, helping scientists identify substances with high precision. Bohr's model laid the foundation for understanding atomic behavior, bridging classical and quantum physics. It showed that electrons are not just tiny particles orbiting the nucleus but follow specific rules governed by quantum mechanics. The discovery of atomic spectra provided direct evidence of these quantum rules, proving that atoms are not chaotic but follow an elegant and predictable structure. Despite these limitations, Bohr's model paved the way for the development of quantum mechanics. The concept of quantized energy levels introduced by Bohr was later refined by the wave-mechanical model of the atom proposed by Schrödinger, which treated electrons as wave-like entities instead of point particles in fixed orbits. This journey from early atomic models to quantum mechanics highlights how science evolves with new discoveries. The study of atomic structure is not just about understanding atoms, it is about understanding the fundamental nature of matter itself. Thank you. Keep exploring, keep questioning, and keep learning. Stay tuned to Ask Prep for more insights into physics, and best of luck with your NEET preparation.